Warning! I risked my life making this video. Household electric installation voltage poses an electric shock hazard and can be lethal. Do not try it at home. Hans Christian Ampersen. Electrifying Fairy Tales. A great while ago, when the world was full of wonders, there lived a voltmeter whose dream was to be invisible. And this dream had a strong merit. Let me explain. Here I have a 2-cord extension, a power block with a switch indicating when the power is on. The voltmeter shows 121 volts AC. Now, I take the extension and plug it into just one slot of one of the outlets, the live one. The neon tester illuminates, but it is hard to see in full lights. Anyhow, the wider slots in the outlet are neutral. The short ones are hot. I measure 121 volts between those two, and now I leave one sound in the neutral, and using the second I touch the exposed prong, which is not connected to anything. And here I have 115 volts. I touch it with my finger, and I'm not zapped. The voltage between the neutral and the end of the extension cord is 120 volts. And at the second outlet, I have 115 volts. The neon tester indicates the presence of a dangerous voltage, but I can touch it without being electrocuted. What is going on here? This meter will answer this question. It is a clamp meter that is used to measure a high amperage current, but it has also built-in other functions. Same as the previous one, this one measures 121 volts in the power bar and 115 volts between the neutral and unplugged prong. Now I set the voltmeter to LowZ function. This time, between the neutral and unplugged prong, we have over 28 volts. While the voltage at the power bar didn't change. Why the difference? The difference is due to the internal impedance of the voltmeter. Let's see what is the internal impedance of the voltmeter at the regular voltage dial set. It is 11 mega ohms. And now let's see what it is at LowZ function. It is over 292 kilo ohms. When I plug in just one prong into the live point of the outlet, the other, not connected anywhere wire that runs parallel to the energized, forms a kind of capacitor with the first one. It has capacitance of only 2 nanofarads. But can we see it in real life? Let's say that I have a breaker box and many wires run from it parallel to each other. A wire can be disconnected from the breaker, or is loose or burned, and forms an open circuit. But somewhere in the house we can have voltage indicated by a neon probe or a voltmeter. But when we plug in an appliance, it doesn't work. The voltage disappears. This we call phantom voltage. So when the voltmeter with high internal impedance can fool us, why do most voltmeters have high internal impedance? Only in some special situations do we need voltmeters with low internal impedance. In general, we will rather benefit when the voltmeter's internal impedance is high enough to make the voltmeter invisible for a tested circuit. Consider a circuit that consists of two resistors connected in series that is energized by DC voltage. This will simplify the matter, and we will be talking about resistance here, not impedance. DC circuit, we talk about resistance. AC circuit, we talk about impedance. The voltage that is supplied to my circuit is 10 volts, and for now, I don't care about polarity. Each of the two resistors is 100 ohms. According to the second Kirchhoff's law, voltage drop on both resistors is the same and is equal to 5 volts. I like to measure the voltage drop on one of the resistors, so I connect in parallel a voltmeter. Unfortunately, the voltmeter has an internal resistance of 300 ohms. Obviously, it is very low internal resistance, and it is hard to find such a voltmeter. But I use this value to deliver a point, so bear with me. I can substitute this parallel resistance with resistance Rw, and in this case it is 75 ohms. According to Ohm's law, the current flowing in this circuit is 57 milliamps. Voltage drops on resistors R1 and Rw are 5.7 and 4.3 volts respectively. As you can see, introducing the voltmeter with its internal resistance to the circuit changes voltage drop values. This is not good. An ideal measuring device should not affect testing circuit parameters. What value of internal resistance should the perfect voltmeter have to be invisible for the circuit? This combined resistance Rw should be as close to R2 value as possible. When is it the case? When the internal resistance Rm is approaching infinity, then the R2 by Rm is close to 0, and the whole expression is very close to R2. Therefore, the perfect voltmeter's internal resistance is infinity. We are not living in a perfect world, and in most circumstances, internal impedance of 10 megaohms is more than enough to make the voltmeter invisible for the tested circuit. But when we measure the voltage of an open circuit, then we prefer this impedance to be low and act as a load. Here I have an example of a multimeter that can measure DC voltage, AC voltage, and battery voltage. Hold on a second. A battery is DC voltage. Let's measure the internal impedance of each. The internal impedance of the DC voltmeter is 10 megaohms, and of the AC voltmeter is about 8.5 megaohms. For the battery voltmeter, it is only about 152 ohms. take a look at this. The open circuit voltage of this battery is 12.8 volts. When I introduce the tester load and force the current of about 90 amps to flow, the voltage drops to about 11 volts, which is a good value for this specific battery.
Daddy, can a small voltmeter measure a big current?
Go to sleep, my son. This is the subject for another story.